Good evening, everyone. Welcome to Brahmagupta Colloquium. Our guest speaker for today is Professor Gautam K. Samanta. So, before we begin, I would like to introduce him with few lines. Professor Gautam K. Samanta received his UG and PG degrees in optics and optoelectronics from the University of Calcutta, followed by the PhD in photonics from the Institute of Photonic Sciences, ICFO, Barcelona in July 2009. He then joined PRL Ahmedabad in October 2010. His research interests includes structured laser beams, nonlinear optics, quantum communication, and quantum sensing. He has more than 150 technical contribution in journals and conferences. His recent results have been highlighted in OSA, OPN, along with a cover page by APL Photonics. He is the recipient of the award of International Commission of Optics and ICTP. He is a senior member of OSA, an editorial board member of the Journal of Optics, and guest editor of Journal of Optics and Journal of Physics B. Besides his regular research activities, Professor Samanta promotes optics and photonics among school and college students as well, covering more than 50,000 students in various states. We are very happy to have him here today. I would like to request him to please come up and begin his lecture. Thank you, sir.
Good afternoon, everyone. Thank you for the introduction. And before moving to the talk, I should thank Professor Prem Beast and Madam Prof for the kind hospitality, invitation, and the opportunity to talk. So I'll be talking about the bright entangled photon source. The definition of brightness will change depending upon the field, and that to use in quantum communication and quantum sensing. So, a bit advertisement for the group. So, we have this is the laboratory front gate. So, in case you have not visited, I'll request you to visit. So, we have a set of bright people. As you can see here is a bright attire. Okay, they love playing football and other thing. And sometimes they come to the lab and really work hard, for which I am here and presenting in front of you. I am also thankful to the collaborators, those who have really extended their support throughout the years for the development of the activities that I have been doing. Okay, so in nutshell, if I have to explain what are the things we have been just doing, that can be basically just shown by this graph. We are having this Gaussian laser beam. We manipulate the spatial structure of the beam to convert into a structure beam. We study the structure beams. We take these two kind of beams, let's say Gaussian or vortex or any spatial structure beam, do the nonlinear interaction of those beams, generate new wavelengths, new structure beam, polarization entanglement, orbital angular momentum, orbital angular momentum entangled states. Those are the things we do. And then we use them for quantum communication sensing. And recently we have started also payload development that this entangled photon source can be sent to space for its performance study, so that in future when you are looking for satellite-based quantum communication, then we are ready for that. And we have also a program for prototype development, so that this entangled photon source can be packaged and that can be used for some others. Okay, so to give some brief outline about the activities in quantum optics, we have this free space channel to test the free space QKD. We also work with a single photon for basic experiments. Here you can see this is the interference of a photon with itself. So this is the interference pattern of orbital angular momentum carrying photons, and it's a vortex kind of structure. It's an integrated one, what you are seeing in case of classical domain or classical laser field, you see similar kind of interference pattern. But if you are having also single photon, that you can see this kind of interference pattern. So this prototype, and then we also try to improve the performance of the system, so that it can be used for outdoor experiments, payload, and we also implemented this free space QKD in collaboration with Space Application Center ISRO for quantum secure video conference activities. So then we are talking about the communication. Then I thought, let's say, what is communication and when it started? So if we see that Google gives this kind of information, the communication started, that is documented one, goes back 30,000 BEC or something, when people used to draw cave painting or stone carving kind of thing. After that, there is a significant change in this mode of communication is something we old people have seen in 80s movies. Pigeon is taking the message from one point to another point. That is basically, if you just see in dated back 776 BCE, at that time people used to have that. Then the significant, because all this milestone kind of progress in case of communication is the marathon man. So today we do the marathon. There is a nice history about this. It is to commemorate the person who ran from Marathon to Athens to declare the defeat of Persian to the Greece. So, but that guy, after conveying the message, he died due to the exhaustion, because he had to travel 40 kilometers all the way from Marathon to. So for that, basically, they have started this marathon race kind of thing. That is how it evolved. Then the common era is there. After that, this first newspaper, telegraph, and so on and so forth. And nowadays, there is more ways of communication than the message itself. That's why a lot of people can really just have the luxury to convey stupidity and idiocy with this kind of communication, since it has evolved. Okay, so this communication has evolved. When communication is evolving, some other things also evolve at the same time. We all have that kind of thing to hear somebody else, unintended information we want to hear from others. So King used to do this kind of structured development so that they can hear what people are just, if there is anything against him. Not that information you have to hear. Sometimes you have to see, to collect that information through a painful way that you have to access, or you can just listen also in the closed door. Then the World War II, when you can see, and then sometimes this different way this people is being hacked or monitor their communication channel, what we can see today. So that's why communication was improving, mode of communication, and then eavesdropping was also improving. So people have just come with that cryptography. So that is what Spartan skytail kind of thing, scissor shift, and then the significant one is the RSA algorithm. What we today in current time we use this for cryptography, and then many other things has happened, and then we are just in the quantum communication domain or quantum cryptography. So now the question is, what is quantum cryptography? To understand that, first we have to start with infinite monkey theorem. So it states that if you encourage a monkey, I don't know how you can encourage a monkey. Okay, if we can do, that is a different topic. If we can encourage a monkey to hit the typewriter is given, and then hit the typewriter randomly, then there is finite probability that he can create whole Shakespeare's creation. The probability is there, it is not zero. So, yeah, so I saw many monkeys, but I couldn't really encourage them to do that. And they need also laptop at that time, because typewriter is old fashioned, they might not really like it. So, yeah, to just come back, basically, perhaps the time it will take will be more than the age of universe or so. Now, if the monkey do PhD and postdoc and then get a faculty position, perhaps his knowledge goes up, it will take less time, that's perfectly all right. But that is what it's saying. Say, now, why I'm just giving the example, let's say today's cryptography is based on this kind of principle. What we say, let's say if the monkey is the hacker who is improving its knowledge, and the message is what we are encrypting is Shakespeare's creation, then there is always a fight. So one is improving, then I have to improve, like that. Okay? So to avoid that, one day, basically when this quantum computer come, then nothing will be secure. So that is what people are just afraid of. And then this new field evolved because people wanted to really just make that one. So what it says, so the key, quantum key, or the key is being generated using the principle of quantum mechanics, which says that you cannot really copy anything, any unknown state with 100% fidelity without being detected. So if you are just trying to copy, you will be just you will be detected, and that can be done. So now question is how we do that. We can use, there are many ways people do, but the one I do is basically entanglement. Okay. So then question comes, what is the entanglement? So just to give an example, what is the entanglement? Let's understand something, a very simple way I'll just put in this. Let's say we have two coins, unbiased coin, and I have one coin and I'll give you, any one of you, a coin. And then if you toss the coin, then there is a probability that 50% time will get head or tail, irrespective of whether you are doing or I am doing. But there is no correlation between our toss, because if I get head, there is no certainty that you will also get head. You might get tail. So that is not a correlated one. Now, if you keep a unknown string, let's say somehow connect that unknown, it's an invisible string. Both the coins are connected, just establishing some correlation. Now I toss the coin, it becomes head, and then your one also become head. So if you just somehow adjust that or manage that, then when I toss, it has equal probability of head and tail. It's a superposition state. But after the measurement, when it falls on the ground, I see that in the head, and immediately the other one collapses into the head, because due to the correlation. Okay. Now, if somebody take the coin from you and replace with the identical coin and give it to you, then what will happen? The correlation what we had established, that will be lost. So you cannot really just, and immediately you see that one, okay, if I toss, that is not happening, that means somebody has compromised. That is the principle what we just use in case of QKD. So we use that correlation to establish the security. If somebody try to tamper it, we will understand whether somebody has done or not. But coin cannot be really just used for communication from here to there. Perhaps in a few meters we can do that one, but let's say for that we use photons, and that is what we actually come into picture, and many others are there. Those who work with photons. So how you do? Let's say to understand this one, I can just put in this way. So you use nonlinear interaction, that I'll come into the my talk. So we send a photon to the nonlinear crystal, which splits into two photons of two different energy, and the total energy of these photons will be the same as the input energy. Now, these photons maintain correlation in different degree of freedom. So let's say in the polarization, energy, or spatial mode or something. Let's say for that example, for this example, simplifying this one, we keep that correlation in polarization basis. So I send a photon, and the generated photons become horizontal. So horizontal polarization, and then another photon is horizontal. If it is becoming difficult, so let's say red ball and red ball. So I give it to someone, another one is getting another guy, those who are trying to do the communication between these two. It's a red ball, red ball. I can create again a green ball, two green balls. So I can just send green. So you see that it's a green, so the other one will be green because they have a correlation. Now, if I randomly generate that red and green, I don't know how it's being generated, but it's randomly generated. Nobody can really predict that. So that means, so you don't know before the measurement whether it's a green or red, and the other guy also doesn't know whether it's a green or red. So you take the measurement, it's a red, then the other one is definitely red. It's a green, other is a green red. So that is how we do. Let's say in case of photons also horizontal or vertical. So if you can just to make this even interesting or improving this performance. So what we do, we take that ball and we put some reflector, which 50% chance it will reflect the ball and 50% chance it will transmit. Okay. So the transmitted one become, let's say, red and green. There is a two detectors I put. So the red ball comes here, green ball comes there, and then reflected one, we make it a complementary color. Red becomes cyan and green become magenta. So then I put two more detectors, cyan and magenta. So one ball goes and it will land someone or the other. So let's say it goes to the green. Similar thing is I'm just doing for the other party. So put two parties having 4 detectors each, and third party is sending the photons or balls. Now, you know when this detector clicked, then automatically we know that when this collector should click. If somebody make some changes, then this photon will not click to this detector, it can go to some other detectors. That is how basically, just you establish the correlation, and from there you find out what is the right number of clicks to what is the wrong number of clicks. That is how do we generate quantum bit error rate, and from there we establish whether the quantum bit error rate is less than 11%. That means if it is lower than that, there is nobody who is tempering that one. That is how we do. So using that, we have in Space Application Center, between two buildings, we have established, we made that entangled photon source, took there, and then established this communication. And once that key was shared, then we do the classical communication and encrypt it with this quantum key. That message is there, so we can just establish that. And it's not that we are the only people, those who have done, and we are perhaps, just starting, and different countries has made significant progress in this direction, and free space or fiber links. And one of the leading countries is China, who is making these things. So this is one. So for this quantum communication, I perhaps just convince you that I have to create the photon source to establish this communication between two parties. So that photon source, I will be just talking what I just gave in the title. Now, if you have that kind of photon source, can you just use for quantum sensing? So that is what basically, just when we are talking about sensing, like optical coherence tomography, where we take a laser beam and let's say the sample and interfere. Let's say classical laser source is coming, split at that, and then you just make a interferometer and then detect that. So depending upon the phase or due to this the sample, the interference pattern will shift, and from there one can measure, let's say, measure the refractive index. So in this case, the refractive index one can measure is less than 10 to the power minus 3. Okay, so the resolution of this kind of measurement is in case of classical domain, it's 10 to the power minus 3. You cannot really go, because the interference fringe width basically decides whether you can just make the measurement higher resolution or no. But for that, one has to use a broad spectrum. So let's say I have the classical source whose spectrum is very broad. So then the fringe width will be very small. So in that case, you can just improve the resolution of this measurement. But unfortunately, what happened, due to the dispersion of the medium, you cannot really just increase this spectral width of the pump or the laser and the resolution of the system. So, but in other cases, let's say in case of quasi-phase matching crystal or some crystals whose phase matching is changed by changing the temperature, their value changes in the order of 10 to the minus 6. Or let's say phase compensation to find out exactly what is the length. So those numbers or multi-core fiber design, there also the refractive variation goes in this range. So we cannot really just use classical thing. So now we try to understand whether we can just use quantum source or quantum mechanics to understand that quantum, let's say, improve that sensing accuracy or resolution. So I have been telling about this photon source. How do you generate? So it's a very simple cartoon. One photon goes and then to the nonlinear crystal, and then parametric interaction happens. It generates two photons whose energy, it follows this conservation law. It's both energy of these two photons will be equal to the energy of the pump photon, and they also maintain the momentum conservation. So you have to maintain the major momentum conservation, because the wavelengths of these interacting photons are very different. So that's why you have to just make that momentum matching to get sufficient conversion or the energy conversion from pump to the generated photons. Okay, so there are many ways. I had time in the morning to discuss with the students also, like type 0, type 1, type 2, type 0, and there are different techniques one can use. So let's say in all the cases, we can just have this kind of special distribution of the photons for degenerate photons, down-converted photons in case of type 2, type 0, type 2 or so, type 0. So if you are just to give an example, let's say the pump photon goes through that one, it creates a down-converted photons. One is vertical, another one is horizontal. So now if you collect a photon from here, immediately you see its partner is lying here or other point or anywhere. But if you collect the photon from this point, you don't know whether it's coming from the green line or the red one. So if you see it's coming from the red line, so another intersection point will always tell that it is coming from the green. So if it is from the red, it will be green, or if it is green, that will be the red. So basically, in this case, these 2 points, the state of the photon or polarization state of the photon, we cannot really write as a horizontal or vertical. Rather, we have to write in the superposition state of equal probability of this plus this and this plus that. So that is what we basically just always create the ambiguity about the state. So entanglement is nothing but the ambiguity. We don't know whether it's which one is that, and that ambiguity gives the sense of entanglement. So since we cannot say which way it's coming from, we say that it's entangled. Now, if you have just entangled, that is what you can see in the lab, and this is EMCCT recording, and then you can see exactly what is that ring. Now, if you have this source, now what you will do, you will basically just use 2 detectors and then collect the 2 photons, and if they are coming at the same time to the 2 detectors, the detectors will click and we see that coincidence, and that is how we just create, and then we do measurement of Bell state, entanglement, tomography, and many other things to confirm whether it is there. But in lemon thing, it will be something like this one. So there will be a interference change. Let's say if you just keep the polarization state of one of the photon is fixed and keep on rotating the polarization state of the other photon, then the coincidence will keep on changing. And from the visibility of this coincidence interference, we can just say whether it's say a Bell state or not. Okay, so that's fine. So that is what we do. But now, when we are talking about this entangled photon, and I'm just talking about the single photon. So what should be the number of photons one can access? Because let's say if we are just trying to communicate from one point to another point, and their losses are involved, we have to really just start with large number of photons at the initial point. But again, large number of photons, if you're just trying, then the quality of the entanglement goes down. So we have to just find out whether we can improve the performance of the source or the brightness of the source. So for that, basically, since I'm just working with the parametric process, so we have to increase the parametric process, because parametric gain is a very, nonlinear process is a very feeble process, and then parametric gain is very low. So one has to increase that, one can increase this parametric gain by increasing the length of the nonlinear crystal. So you take a longer crystal, and then parametric process will be stronger. But in that case, when you are just doing this one, this spatial walkover comes in picture, because the photons, what you are generating, even though their wavelengths are the same, but the polarization states are different. So in that case, there will be a spatial walk-off. So to get that spatial walk-off, people have just gone for the periodical pole crystal. But again, in case of periodical pole crystal type 2 phase matching, where the nonlinear that polarization states are orthogonal, so in that case, you will see this problem again, that walk-off. So normal means basically, if you are just trying to get that highest nonlinearity or highest conversion efficiency from a nonlinear crystal for pair photon generation, one has to use the type 0 process, and which is relatively very high. So that is what we are just trying to address that. But unfortunately, when you are just doing this, then this process, the polarization state of the photon is same, their wavelength is same. You cannot really separate them, because there is no way you can use to separate the signal idler or pair photon. So that is why nobody really just tried to do that one, because you cannot, even though the gain is very high, you cannot really separate the photons. So that is what we just came up with, this non-collinear geometry, where you can just spatially separate them, or you can just change the phase matching condition in such a way that the photons will be spatially separated. So that is what we do. So let's say we take a nonlinear crystal, I said, and here is a collinear geometry where the down-converted photons are propagating along the same line. That's why we are just seeing a spot. But then if you just keep on reducing the phase matching condition, or if you reduce the temperature of the crystal, then this photon will be spatially separated, or it will be coming in the annular ring. So any point in this one, diametrical opposite points are the pair photons. So you can just select from here or anywhere with that, so that you can just get that pair photon. So now all the photons having the same polarization state and same wavelength, but they are spatially separated, so we can really use it. And that is what is phase matching condition, how that change. And if you just see this intensity of this one, so when it is in the non-degenerate case, so in that case we just see the highest conversion efficiency, and non-degenerate cases people really just got that very low conversion efficiency. So finally we get this kind of spatial distribution. So if you go to my lab, you will be seeing this kind of intensity pattern being detected for the single photon. So this one is basically is a EMCCD image where single photon events are being collected and integrated for a longer period of time. So now if you collect any photon from this point and it's a diametrically opposite point, they are the pair photons because they are just maintaining the phase matching condition and it has to be in that one.
Frequency are same, right?
Or frequency is the same.
Wavelength of frequency.
Wavelength is same, polarization is same. That's why we are just going to that in a non-collinear geometry, otherwise you cannot really separate. So some people have just tried to put a beam splitter and then split them. So, but in that case, you are losing many things. So that is not a very efficient way.
What is the difference between pair photon and entangled photon?
Okay. Pair photon is basically generated. Okay. So here, these are the pair photons. Because one photon goes and then splits into two.
Yeah.
And since this phase matching is satisfying the vertical polarization, so pump is vertical, horizontal is vertical. Okay, so to make it entangled, we make that vertical and horizontal combination. So we have to just generate another pair where, like you will put two crystals, you don't know whether it's generated in the first crystal or the second crystal. In the first crystal, it will be horizontal, second crystal is vertical, something like that one. Or let's say if you are just considering type 2, where signal, because they are degenerate.
Yeah, they both have both
same,
entangled and pair.
So they are exactly because they have orthogonal polarization, but the signal can also be horizontal and idler can also be horizontal.
Okay.
So another one will be vertical. So that is how we just as a play with that.
Okay.
So that is why I am just talking about the pair photon because in single pass that is what is being generated here. No ambiguity is there. It's always a horizontal same state.
Okay. Thank you, sir.
Yeah, thank you. So, but the problem comes basically even you have just selected the photon from here, and this ring size basically as I showed, the size of the ring is dependent upon the temperature of the crystal. So that's why if you just select the photon from here, to give an example here, let's say this is the SPDC ring, what I am just seeing, and then at 25 degrees centigrade, my detectors are aligned so that it's collecting exactly the photons from here. But if we change the temperature of the crystal, then you can see the ring size goes up here and there. And in that case, you cannot really collect the photons, and that will be useless. Okay. So given these things in perspective, let's say if we have to, this is what is basically coincidence is recorded as a function of temperature, and you can see to get 10% variation lower than that, the temperature of the crystal has to be within this range, 0.12 degrees Celsius. It's a pretty large requirement in terms of basically if you are just trying to go for outdoor applications where the source can have some external resources are low, or if you are just trying to go to space where maintaining the resources is expensive. So in that case, basically it's creating problem. Yeah, we have set. So you can set your detector for that temperature. You can set it anywhere. There is no speciality about it. You can take that one. But for an example, for 25 degrees centigrade, we have set it. That crystal temperature at 25 degrees, my detection system is fixed. Now, if there is any change, then your detection will be, because collection will be lost.
So in terms of physics, is a nonlinear coefficient changing with temperature?
No. Here, all these things, because we are in the zone of, because temperature of the crystal doesn't really change your nonlinearity. Here, basically, just K value is thing. So if you go for higher K, then perhaps something can happen because some reduction is there. But here, the temperature range you are talking about, that doesn't change. One thing. Second thing also, what you said correctly, you see, the number of photons generated is fixed. Now, if you distribute it over a big ring, then the photon density being collected will go down. That's why the photon density being collected for this detector will go up if you are just going towards the degenerate case, because the photon density is, you are basically just n number of photons being distributed over a small area. That's why, when we study this, we have to select the zone where we want really just higher numbers. Otherwise, there is absolutely no problem.
So will it go like a cone as you move
It's just a cone. It goes out and thing. Okay. So what do? We just split them and then propagate them in two direction and then collect using this detector. But what I'm trying to point here is that, let's say you fixed. So you set the temperature, everything is fixed, and the detection system is fixed. And then if something happen, some change is happening, not in the crystal temperature, but also let's say change in wavelength, because laser wavelength is, it's very difficult to stabilize the laser because there is random mode hops happens in case of laser. So perhaps it's not happening, you are seeing, but sometimes it can happen. So in that case, we realize this SPDC ring also change because your wavelength is changing, the phase matching condition is changing. In that case also, so if you are just setting here, that is what you see, in either side you will be just reaching to this one. To avoid this, we try to make that one, this ring as a perfect ring. So whatever the change is happening, I don't care. Any change is happening, but my ring need to be perfect in shape. So its size remains unchanged. That basically we do in structure beam. So if you take a vessel beam and then do the Fourier transform of it, you will convert that input beam into a ring shaped beam, and which is independent of the change in the input. So anything happens in the input, the ring size remains unchanged. So as you can see here, this is the experimental thing, kind of, let's say changing the temperature, you see the ring size unchanged, the wavelength is changing, but still the ring size is unchanged. So you are basically just enhancing the tolerance to the system of the system. Okay. So now if you have this, the source, that's a single photon, pair photon is there, and then we try to interfere these two photons. Let's say we have generated the photons and then take them and then put on the two input ports of the beam splitter. That is what you're saying, one input port, another input port. So if it is following, and then we are just two output ports, we are just putting two detectors. Okay. So what it can have, we can have all these four probabilities. One is that one photon is reflected, another photon is transmitted, plus both the photons are transmitted, minus because of the phase due to the reflection. Both photons are reflected, minus it can also one photon transmitted, another photon reflected. These four possibilities are there. Now, if the photons are identical in all degree of freedom, then these two probability will cancel out. So, and these two probability basically is because the one photon is coming here in the output, second photon is going into other output, or if it is reflecting, then the same thing, and these two detectors will show the coincidence when they detect the photon. If one of the detector is seeing the photon, then there will be no coincidence. Okay. So when the photons are almost identical in all degree of freedom or time, then in that case, these two will cancel out and we will left with this and this. So in this case, both the photons is bunching to one of the ports. That's why you don't see any coincidence. Then what happens if you just measure the coincidence with the time delay? So you just put that one of the photon in the delay stage, you delay it, and then measure the coincidence. You will see that deep. This is called HOM interferometry or Hongo-Mendel interferometry. So basically, at this point, so only these two probability of getting both the photons in one of the ports will be there. So which leads to no coincidence. But when you go away from this, then these probabilities will be dominating one because the photons are coming at different times or something. So in that case, you will see that coincidence. Now, this is what it has been there for a long time, and people are just trying to use this for sensing applications. So let's try to do the sensing. What hot sensing we can just do? Now, I said that this delay is there. Any physical parameter creating delay to the photon, that can be detected. So if we are just delaying, so there is report that one can detect or measure the delay of the order of attosecond. If you are just introducing attosecond delay of these photons, so that can also be detected using this kind of geometry or interferometry. Okay, that is what we have just used. Let's say the laser taking that and then nonlinear crystal is generating photons that is split in two arms. And here one of the photon is being delayed and it's falling on the beam splitter. That is what I was just talking about. And then we are seeing these photons in the two arms and then finding the coincidence. Okay, the photons are coming and then it's being detected. Now, if we just keep on changing this arm, because we are just adjusting the delay between the photons, then we will, so then we can sense and measure that one. So before going to this one, so let's say this intensity distribution, what I showed previously, it's having this in this formula, where this delta k is the phase mismatch, which can be represented in this way. And if you just do this Taylor series expansion, it goes in this one. So this first term is basically we just adjust because it's a phase matching condition. Second term is the group velocity mismatch between the photons. So once the photons are of the same wavelength, then the group velocity is 0. So in that case, the third term will be a dominant one. So that is called group velocity dispersion. So in that case, the generated photon spectral width. So what should be the spectral width of the generated photon? That is represented in this form, where you can see the spectrum of the generated photons will be 1 by square root of L. So basically, just reduce the length of the crystal, you can go into increase the spectral width of the generated photon. And if you increase the generated spectral width of generated photon, then the width of the HOM curve, what I showed, will keep on reducing. And if you see, so if you reduce the width of this HOM curve, then you see the sensitivity, because its gain is increasing, because any small delay here will give a large variation in the coincidence count. That is what we are just trying to show. So that means we need really a bright or a broad spectral width of the generated photon that we can just use using a different crystal length. That is what its HOM curves experimental measure. For 30 millimeter crystal is a purple color, and black one is coming with that 1 millimeter crystal. Now the question is coming, let's say in 30 millimeter crystals, since the parametric gain will be very high, your generated photons will be more. But 1 millimeter crystal, your generated photons number will be very small, but the number is substantially large for in case of application. So if you just translate this graph into numbers, basically the crystal band line with the crystal width, crystal length, the spectral bandwidth of the down-converted photon going down from 163 nanometer to 30 nanometer, as a result of which full width of half maxima of the HMDV is increasing. So that means, this is the domain for which we can really use this domain for any application or sensing application. So that is what we just try to do. So if you can just see here, any small fluctuation we give because of this slope is very high in case of 1 millimeter crystal. So we can get substantial large variation in the coincidence count, that for sensing, than this curve. Okay, so that is what we are using. So using that, then what we did, we just put the delay stage and then displace the mirror by 50 or 60 nanometer. That is what all 60 nanometer kind of displacement we are just talking about. And you can see there is a substantial change in that counts, coincidence counts, which one can detect. And that is what we are just seeing. There are straight lines coming with time when we are just, basically we are just delaying 60 nanometer, 60 nanometer, 60 nanometer like that. And then we see that these two coincidences are not overlapping with each other. So we can clearly measure that displacement by 60 nanometer between the two photons. And 60 nanometer, if you translate it into time, it will come in the attosecond time scale.
What was MNK in your Taylor series expansion?
Oh, they are here. Yeah, that is a group velocity coefficient. It's a coefficient, and there is another coefficient. This is a group dispersion, so it comes. So that is what is static displacement. So then we thought, let's try to do something which can give you more in terms of dynamic sensing, because nobody really has done that kind of dynamic sensing, whether this can be used to sense any displacement with varying time. So for that, we have a piezo, and that we have characterized. So just playing with the applied voltage and then characterize that. So using that characterized piezo, we see, you can see here, this is what it is happening, what I have been saying. Let's say 1 millimeter HOM curve, if we are just seeing small amplitude to the piezo, so then we see that variation in that coincidence count. And from there, if you take the Fourier transform of it, we get the frequency, and that frequency is something around 8 hertz. After 8 hertz, the peak, because the intensity of this Fourier transform component is low, so we can really reliably measure. So we can go up to, let's say 8 hertz frequency, which is almost close to that video range, because basically it's not, the interesting point is this 8 hertz we are saying, let's say when you are sensing, let's say imaging of this one. So you can sample eight sorts or positions of the sample because it's 8 hertz. Okay. Otherwise, normally people used to just wait for some time one and then going to the next one. So it takes time. So it is a faster way of doing the imaging or sensing. So, and then we can measure this kind of values. Let's say if you're just having this kind of displacement that reliably we can just produce. And then we did also just give some arbitrary signal. So that is what whose frequency is changing, amplitude is changing, and you can see the coincidence count is exactly following that kind of change what we have applied. So that is what it's clearly showing the reliability of the system. Because in this case, even though the photons are having a broad spectrum, but the dispersion doesn't really play any role to change the performance of the system.
Sorry.
Yeah.
Can you attribute it to quantum fluctuations or thermal fluctuations?
Here, actually, we are displacing the delay. We are changing the delay. So as I showed here, so this is basically this stage is there. This mirror is there. Okay. So first we are characterizing it. So let's say whether it's performing the way we want. So we put this mirror on a stage which is being fed with a applied voltage, and that is a dynamic signal, and that dynamic signal is arbitrarily changing. So then we are seeing this change, how it is translating into the coincidence variation change. Okay, so that is what we are modulating like this. That is what it says, a displacement of the piezo. That is what with the applied voltage with time we have done this, and then here we are measuring the coincidence counts. So then we see the one-to-one correlation. That means it's clearly saying that it can do the dynamic sensing. That is what we are just trying to do. Okay.
In case like piezo, something moves, then that can be
Exactly. So that is what this is here. This one is a part of the project of this seismic activity measurement. So before that, we are just characterizing it to see whether we can do it or not. Now, that kind of spectrum, but that is basically displacement of something around 60 nanometer in that range. You can, but again,
your whole thing will move actually. Your setup.
no, you have to just put that on one beam. Another beam has to be in that direction. Direction wise, you have to just adjust.
Yeah, I mean, if you go back to your setup.
Here in the lab, we are just doing for that particular.
Intentionally doing M2 movement.
Yes, yes.
But in case of sensing real time.
Yes, yes.
Because in earthquake, your lab will also
Move. Yes. So then you have to just find out the direction, which direction I have to just put with respect to the other one. No, I'll not enjoy that. I will just rush out. Okay. So letting that system to take its own health care. Okay. So, okay, we have just reached to that point, and then we see this one. And then we try to see that, okay, this one is basically dynamic, because when you are doing dynamic, it have to be really a faster process. Otherwise, if I ask you, I'll give you a data point after 2 days, okay, recording that measurement, then you will not really like. So that's why we try to address that. It's immediate. Now, then we try to say that exactly if you are allowing me 2 days time to do the experiment and then saying that what is the lowest one you can go, then we will do this kind of thing. We'll do all the possible statistics on that and spend time. It's basically, just what is the lowest we can just go ultimate limit for this precision, that is camera roll bound. So here is a number of iteration n, and f is the Fisher information. So for that Fisher information, you can just see for type 0 crystal, the process what we are generating. You don't need to really go into details of this one. Just follow my words, then perhaps it will be easy to understand. So there is some Fisher information formula. It goes with the length of the crystal. So if you just reduce the length of the crystal, then the Fisher information goes up. And if your Fisher information goes up, then this bound can be saturated with lower number of iteration. That is what we are just trying to say. So if the product of these two numbers is fixed. So if you can somehow increase one number, then other number has to go down. That means if the number of iteration is lower, that means I can do it faster measurement. That is what we are just trying to do. Basically, just to lower saturate the bound by playing with the Fisher information, which is a function of length of the crystal. So basically, we are just reducing the length of the crystal, and then these are the parameters basically defining this Fisher information. The more important thing is basically the length of the crystal. So then if you just calculate the Fisher information for different length of the crystal, as you can see, as expected, for 1 millimeter crystal, the Fisher information peak is something around 17 times more. It's something 17 times enhancement. That means my number of iteration goes down by 17 times. And since iteration time is, let's say, if it is taking 1 second, then my time, overall time, will be smaller or something like that. Basically, the previously what people have just reported using Fisher information based sensing, there they have taken whatever numbers they have just taken. It's something around hours, but we are just going to the minutes. Perhaps in future we will go into seconds kind of thing to give you the real time high precision measurement. So this is what peak value of this Fisher information goes like this one with the smaller crystal. That is the interesting point where Fisher information goes something 35 10 to the minus 4 per meter per micron square. And then once we have measured that, calculated the Fisher information, so we use this maximum likelihood estimated function. Basically, we just put this mirror in two positions, x1 and x2, which is separated by 5 nanometer. Okay, so we put a voltage that goes to point A, then it goes to point B. They are separated by 5 nanometer. So then we just likelihood estimated we calculated from the coincidence. So that is what you can see, red and black. These are the 2 points, and you can see there is a 5 nanometer if you just zoom it somewhere. Okay, and then we just find out the different distance separation between these two. And as you can see, initially there is a variation, but after a certain iteration, let's say something around 3000 iteration, it's saturating to the point what we said. So that is basically just a very lower number of previously people used to get that in 12,000, 15,000 kind of iteration, but we are just going into the 3,000 kind of iteration. You can reach to this one, and in that case, you can go to nanometer, 1 nanometer scale or so, using all possible estimation you can do. But that is basically because statistics involved, so it takes time to calculate all these things. Okay. So then we just go with that one number of iteration. As I said, let's say if you are just using 1 millimeter crystal, then the number of iteration goes down. So it's a faster process than the 30 millimeter crystal. So that because of this black curve where peak information of Fisher information value, peak value is changing. Okay. So after setting this one, let's we say that okay, we have talked about many things and we understood how it's performing. Can you now use it for any practical application? So that is what we have just tried to do this one. The generated photons is coming in this way, and then we put a sample in one of the arms, and then we are doing this HOM interferometry. So that is basically we are just trying to do region. So as expected, if you are just putting the sample here, so the peak position will move because the delay between the photons is high in this case. So that we have to adjust. So we adjust this and then come to this point, and then here this is the HOM curve, and then it is displaced. Using this, we can just measure the groove index of different medium. So like this. So that's pretty good. You can see all the points are exactly matching. But if you zoom in, you can see there is a large variation, and you cannot really just go beyond the order of 10 to the minus 4. So by seeing the measurement, like by seeing the shift of this HOM curve, we cannot really do the measurement. So in that case, we basically use the curve of this HOM curve. So we just take one of this arm and then did that temperature variation of the crystal, something like that one. It's changing by 1 degree, 0.1 degree. So in that case, optical delay is changing, and you can see all the points are basically just having separate coincidence counts, easily detectable with the variation of 0.1 degree centigrade of the nonlinear crystal. So that if you take the calculate the measure this groove velocity index, groove index of the medium, so it goes in the order of 10 to the minus 5 or so. Or basically, just in case of let's say broad HOM curve, if you can just take, then in that case you can just increase the range of the crystal. So with this, I think I'm just in time, and I'll be happy to answer the question. So I have convinced you that we have improved the tolerance parameters of the system that can be used for quantum sensing or quantum communication application. I have not really talked about much about this quantum key distribution, because for that what you need we have just discussed. Then quantum sensing we have just done using HOM deep, controlling the length of the crystal. We show that the width of the HOM deep can be changed and then show the dependence of Fi. And HOM interferometer has successfully demonstrated sensing optical delay and then dynamic one. So that dynamic thing is something, just it's we found not many work has been done. So that can give you in the attosecond time scale delay that can be measured. And we have demonstrated also sensing of optical delay in arbitrary wavefront and Fi treatment or Fourier, let's say Fisher information treatment, we can just go to the ultimate precision, and we have shown that low refractive index variation. With this, I stop here and thank you very much.